so I don't forget. So Lisa doesn't have to remind me again. Oh yeah, I didn't share anything yet, did I? You're just seeing my face. Now we're sharing. I'm back. Yeah. All right, everyone. I learned over the weekend that we don't have class on Wednesday and Friday this week. So what does that mean? Well, we finished chapter 7 on Friday. Sorry, chapter 6, unit 6 on Friday. And the other class is like, I don't know, 15 minutes behind us. So they haven't quite finished unit 6 yet. We have, what I really did not want to do was start chapter 7 and then forget about it until next Monday. So what I'm doing today, we're going to do a review of chapter 6. Because chapter 6 is a heavy one, right? We did a lot in chapter 6. We introduced our first 4 reactions, and then, you know, slowly gave you piece by piece of information about these reactions, and then in the end said they all compete with each other and they all can happen in given sets of conditions and blah, blah, blah. That is normally the part in the course that a lot of people pull their hair out because they're looking at it and saying, you know, everything has been sort of small incremental stepwise up to this point, and now all of a sudden we just like unloaded a whole pile of information. And it's subtle and there's complexity to it, and it's very difficult to synthesize all of that immediately, and it takes time, it takes practice, and it takes thought. And today we're going to take that time and practice and hopefully thought, and we're going to go through a bunch of examples of the types of questions, of the things that I expect you to be able to do coming out of chapter 6. And where we're going to be heading after chapter 6, or unit 6, is going to be unit 7. And unit 7 isn't like brand new, completely different stuff. Unit 7 is, we're going to go back and look at those reactions from chapter 6 and discuss maybe some complexities or some additional kind of factors we have to work out. And that's not going to work if you aren't already comfortable with what is being done in that chapter. So together this graphic that you can see on your screen, which summarizes the mechanism outcomes for any possible situation we could throw your way from unit 6. This is all looking at alkyl halides, right? And the substrates can either be methyl, which would be like CH3X, primary, secondary, or tertiary, look like that. And the 4 sets of conditions that we talked about in this course were bulky alkoxides. These would be things like something like that. A small alkoxide, bulkies are tertiary, smalls are primary, ONA. Strong nucleophile would be basically any other negatively charged nucleophile, like, I don't know, NaCN. Protic solvents only. What's an example of a protic solvent? Who can tell me a protic solvent? Anyone? Water, great. Could be like water. Can anyone have a different one? Has to have an OH typically, or NH. Hydrogen bonding, like alcohols, be an example. ROH, I guess we could call it. Or carboxylic acids, RCOOH, where that R is just generic carbon, hydrocarbon chain. And there's a lot of information in this, but you can simplify it if you look at it, right? If it's methyl anything, it's always SN2. That whole top row is always SN2 because you can't do any eliminations because you need a beta carbon to do eliminations. Bulky alkoxides always do E2 unless it's a methyl because you can't do eliminations on a methyl. Small alkoxides also prefer E2 for secondary and tertiary, But if it's primary, primary also, like methyl, primary loves to do SN2. So primary will do SN2 under any condition except the bulky alkoxide. So I kind of feel like if you remember that methyl is always SN2, primary is always SN2 unless you have a big bulky base, which is a terrible nucleophile. And then the other thing to remember is that alkoxides will almost always give you E2. That only kind of leaves the bottom right-hand corner here of stuff you have to think about. So tertiary always will do something that ends in 1, because, well, no, that's not true. It'll do E2, but it will never do SN2, because SN2 doesn't work on tertiary. If you have a strong nucleophile, SN2 if it's secondary, SN1 if it's tertiary. Product solvent won't do anything really active. Product solvent is not strong. It's not negatively charged. It's not a good nucleophile, not a good base. So it does what I would consider the passive mechanisms. Passive mechanisms are SN1 and E1 because the nucleophile or the base doesn't really do anything until the carbocation is already formed. So I'd call all the ones that end in 1 passive. And if you just have a product solvent, it can do SN1 or E1. And the way we're going to demark these two, just to simplify everything, and I talked last class about how you will often get a mixture of these two. If there's heat, it's going to be elimination. If there's no heat, in other words, room temperature or cold, then it's going to be SN1. Now, in reality, you're going to get a mix of the two. You'll favor SN1 if it's cold. You'll favor E1 if it's hot. But just by separating those two this way, I think it'll just make things clearer, and you never have to worry about drawing multiple mechanisms for a single question. Okay. By the way, what I'm showing you today is there's a PDF, well, there's a PowerPoint file that's also been posted on Acorn under like our sections PowerPoints. I think it's just called Chapter 6 Examples or Practice or something like that. So if you're looking for the source of what I'm doing here, that's what it is. Okay, let's go to a first example. For the following reactions, draw complete mechanisms for formation of the major product. Oh, by the way, before I start this one thing I wanted to mention about this, you can see there's little words written under each of these mechanisms. Some of them you may recognize, like inversion. SN2 always inverts a stereocenter. Some of them you may not, like Hoffman, Zaitsev, rearrange. That's coming up in Chapter 7. So we haven't discussed any of those terms yet. I just put them in now because I didn't want to have two versions of this table that updates later. Just the one version. We're going to ignore those words for now, but they will become important in the future. Okay, we want to draw the mechanism for this reaction. Show all lone pairs and formal charges. Include curly arrows where appropriate. So what we need to do, I call this kind of question kind of like the full meal deal. You got to draw everything. I want all the lone pairs, all the arrows, all the intermediates, all the steps, all the formal charges, everything that there is to draw. I'd like to see drawn out there. But before you can draw the mechanism, you have to figure out what the mechanism is going to be, right? So we need to use that table before to figure out what our major product will be here. So what we do first is we look at our alkyl halide. Look at our alkyl halide right here, and we want to decide if it's primary, secondary, or tertiary. What do people think? What kind of alkyl halide is that? Primary, secondary, tertiary?
Primary.
Primary, I got. Yeah, thank you. How do you know it's primary? Because we have an alpha, we have a beta, single beta. It's only one beta carbon, so it's primary. And our conditions here, there's kind of two things, isn't there? CH3ONA, which right away in your brain, you're separating, right? We're separating this into CH3O minus and Na plus. And we should put some lone pairs around the oxygen to complete it. But we also have this. So if you look at our conditions previously, it looks like we have both a small alkoxide and a protic solvent. So then the question might be, well, which column do I look at? Well, if that happens, always look at the column for the one that's more active. You want to look at the one with a small alkoxide. Small alkoxides almost always come in a protic solvent, the protic solvent the alkoxide came from. So here we have sodium methoxide in methanol, right? So they're an acid-base pair. Forget about, if you see this negatively charged thing up top, forget about the protic solvent on the bottom. It's going to be the active thing that's going to force this reaction. So I would say that that would be small alkoxide. So before you can even get started here, there's two things you need to do. Identify whether the substrate is primary, secondary, tertiary. Second, identify the conditions under one of those 4 bins that we had at the beginning. So primary small alkoxide, come back up here. Primary with small alkoxide is this bin right there, SN2. So what we can do is go back to our reaction and say, well, okay, what we want to draw here is going to be an SN2 mechanism. SN2 is the reaction where there's a single step, nucleophile collides, leaving group leaves, inversion. So let's draw that. We're going to start with Br. Our nucleophile is going to be CH3O minus. Bromine, let's give it some lone pairs. We're going to draw all our lone pairs, all our formal charges, and that sort of thing. What's going to happen now is that is going to attack there. I'm going to make my curly arrows red. Doesn't matter which lone pair we start at there, but we need to start at one of the lone pairs. That arrow means that lone pair of electrons is going to the carbon to form a CO bond. At the same time, the CBr bond breaks and the pair of electrons goes to the bromine. All right. Wrong color. That's all. The beauty of this is when you discover that this is an SN2 reaction, every single question is going to look exactly like that, with maybe a different leaving group or a different chain length or a different nucleophile. What that looks like with those arrows, that kind of reaction will always look like that. Wasn't so bad, was it? I think in the example, sometimes we draw in the transition states, right? Like there's going to be a transition state for this that's going to look something like unless we explicitly ask you to draw one, you don't have to. And usually we don't ask. For the following reactions, draw complete mechanisms, same question. Our starting alkyl halide is what? Methyl, primary, secondary, or tertiary? Good, secondary. We have an alpha, we have a beta, we have a beta. What is our conditions? Do we have a bulky alkoxide? Not a bulky alkoxide. There's nothing that's negatively charged here, nothing that's a sodium or potassium salt. So we have no bulky or small alkoxide. We have no strong nucleophile, no negatively charged nucleophile. So we're left with nothing but a protic solvent. That's ethanol, got an OH, protic solvent. So secondary and protic solvent, let's come over here. We're in the rightmost column, and we go down to secondary. And what we see is SN1 or E1 if there's heat. Well, was there heat? That's what this little symbol means. That means heat. You know why we use the triangle to symbolize heat? It's an interesting thing. I only learned that this year. I've been a chemist for a long time, and I only realized, I've heard people wrongly state the reason before, that it's not a triangle, it's a delta, and delta means change, and somehow change means heat. That's not right. It's a triangle because the ancient alchemists, they believed there's only 4 elements, which were fire, water, earth, and air. And they gave them each symbols, and the symbol for fire was a triangle. So we use triangle now for heat because the alchemists used that for fire. So there you go. That little triangle means heat, and that means we're looking at an E1 reaction. Okay. So E1, I mean, you can redraw it down here if we want, and I do want. There's a Cl there. There's also a hydrogen that's there as well. I didn't use dashed and wedged bonds here. You know why? Yeah, it's not an inversion, so I guess I don't have to worry about that anyway. But also, it's also not a chiral center. The dashed and wedged are really important when it's a chiral center. If it's not a chiral center, you know, those two are interchangeable, right? Whether it's front or back doesn't make any difference. It's the same molecule. Okay, E1 or SN1 has the same first step. That first step is loss of the leaving group, right? We have our solvent here, which is kind of weak, doesn't have a negative charge, not strong, anything. So it doesn't really do anything until this thing reacts on its own to make a carbocation. What happens is that Cl bond breaks, pair of electrons goes to the chloride, and what we're left with is we have a hydrogen there, we have a positive charge, plus we have a chloride somewhere. It's floated away. Now, I'm going to come back to this. We have our alpha carbon is the one that had the leaving group. It's the one that has the positive charge. And we have 2 betas, because beta is the one that's attached to the alpha. And actually, we have a whole listing. Like, you can go to the next one. Delta is the next one, I think. Gamma, I forget. But we're in this situation. Chloride disappears, but we have a whole bunch of our solvent, which is ethanol. I prefer to draw it as bond line. You can draw it out, condensed structural formula if you want. This is very ugly, really quick. If you always draw this out, though, as like the big Lewis structures with all the carbons and hydrogens all shown. So it's not wrong to do that, but it's a good thing to stop doing. Okay, so the first step of an E1 is loss of the leaving group to make a carbocation. That's the rate determining step. Second one is the base removes a beta hydrogen. 2 steps to E1. So there's 4 beta hydrogens here. Doesn't matter which one we take, they're all the same. So let's take any one of them. Let's take the one that's closest. And the CH bond breaks, the pair of electrons goes to make a double bond. So we can put that there. And so that gives us there. We still have 1 hydrogen left on that beta, 1 hydrogen left over here. And then we have some other kind of things left over, right? We have Cl minus plus, oh, now this has picked up a hydrogen. So there's going to be a strong acid floating around, but we don't care about that. We've made the product that we want, and the acid is a problem for later. In fact, when we do these reactions, if we don't want that acid to build up, there's techniques we can add base to, like carbonate or something like that, and it soaks up that acid as it forms. but we're not going to worry about it for now. Whatever happens, that's not your main substrate. It just goes away, and we're not going to worry about it. It's in solution. When you do your reaction, we do what we call a workup. We do like a water wash. Anything that's water soluble, often we get rid of. Great. That's how you draw E1. All right. This one. Is our starting compound primary, secondary, or tertiary? Yeah, tertiary. I get like anxious when I say tertiary if I'm saying it right. Tertiary? I don't know. We got B, B, and B. 3 betas. So that's great. Do we have a strong alkoxide here? No. Bulky or otherwise, no. Do we have a strong nucleophile? Negatively charged? Yeah. There we go. Look, KCN, we split that up. We have K plus CN minus. CN minus looks like this. Strong nucleophile, it's got a negative charge. Great. So what does that mean? Let's go back up and find out. Tertiary, bottom row, strong nucleophile. We got SN1. Cool. Strong nucleophiles like to do SN2, but we can't do SN2 on this because it's tertiary. We're going to do SN1. Don't have a base, so we can't do elimination. DMSO. What kind of solvent is DMSO? Yeah, it's a polar aprotic, which is great for SN2, but we can't do SN2. Right? These conditions are awesome for SN2, but our substrate is not good for SN2, so it's got to do SN1. That's all it can do. Okay, we can get over that. Let's draw this thing out. Iodine. Iodine is a great leaving group because the CI bond is weak because they're very different in size. Okay, we're going to break that bond. That gives us this carbocation plus iodide goes off somewhere. If this was E1, a base would come in and remove a beta hydrogen, but it's not E1, it's SN1. And we don't have a base anyway here. Cyanide is like a very weak base. It's a weak base, but it's better nucleophile. Okay, so that's step 1, formation of the carbocation. That's rate determining step. Formation of the cation is always going to be the rate determining step. And we have our cyanide. So this is like the empty parking space. The parking space is empty. And we can now do our attack. Right there. Does that molecule remind you a little bit like of those viruses? Come down with those legs. I don't know. Yeah, bacteriophage. Anyway, yeah, that's it. We substituted the iodide for a cyanide, nitrile now we got, and 2 steps. The even group leaves, nucleophile attacks. These aren't so bad, are they? Once you get the hang of these, and once you realize you're drawing the same thing every single time. Methyl bromide. Primary, secondary, tertiary methyl. Not primary. Methyl, yeah. There's no beta hydrogens. So we know we can't do E1 or E2. We also know we can't do SN1 because you can't make cations that are methyl. So like, this is nice. We don't have to look at our table. We know the ideal is you should never have to look at that table. But that methyl bromide is going to do SN2. That's all. That's its only choice. Okay. And what's going to be our nucleophile? Well, our nucleophile is the solvent, which is a carboxylic acid, which is not a very good nucleophile, but any port in a storm here, we deal with what we got. So we have our methyl bromide. And draw it all out. Small molecule, there's not a whole lot to draw. Draw all our lone pairs. And this is acetic acid. Like this. And we need a pair of electrons to attack here. Go with red again. And we're going to take our OH, oxygen lone pairs, and do our SN2. If you have a nucleophile that's neutral, we have this extra step we have to deal with because we don't like making products with charges. We like them to be neutral when we're done. So when we do this, okay, the carbon inverts, the hydrogens move to the right. I'm going to shut down my email so that doesn't get increasingly annoying. Stop bothering me. Okay. Email's gone. We have our bromide over here. It's gone. And we're attached now. We should, like this part that added on, should look identical to how it looked before, except it's missing a pair of electrons. That pair of electrons is now a bond, right? So we should have the oxygen, the hydrogen, the carbon, double bond oxygen up here, CH3. One of the pairs of electrons is still on the oxygen. The other one that we started the arrow from is making a bond to carbon. Now that's an exaggerated long bond. I should have drew it closer. It's a regular sized bond. But this puts a formal charge of a plus on the oxygen. How do you know? Well, calculate formal charge, right? Oxygen is 6 valence electrons, minus 3 bonds, minus 2 unshared electrons, and we have that structure. Every step, your total charge has to be conserved. You can't add or subtract charges. So, you know, we started with 2 neutral things. We're ending up with a cation and an anion. So you can't make or lose charge. There should be a law for that, law of conservation of charge in the chemical step. I just invented it. It's real, though. Okay, now we need something to pull that extra H plus off. Bromide is not going to do it. Bromide is a terrible, terrible base because it's the conjugate base of a very strong acid, which is HBr. In fact, HBr is one of the best acids we commonly deal with. So we're going to use as our base here, we're going to use another molecule of acetic acid. Acetic acid is not a very good base either. It's pretty bad. But something's got to be a base here. So let's use it. And the oxygen we're going to use as the base is the one that already doesn't have a hydrogen. We're going to use the top oxygen. It's just an acid base step. So this makes and you know, this isn't a great structure here, but at least it's resonance stabilized. Not so bad. Could be worse. And this will be our product. We made an ester, starting with methyl bromide. Methyl bromide, actually, I think methyl bromide or methyl iodide have been used as a pesticide, like an herbicide. We'll take a tractor and spray huge amounts of this into the soil. And what it'll do is it'll methylate anything in the soil that is a nucleophile. So if there's chloride or whatever there, yeah, it'll react with that. But it'll react with like proteins and nucleic acids can be nucleophiles, and it can methylate anything that's alive and has biological tissue with nucleophiles. It'll methylate all those things, which will cause them to die. And the nice thing about something like methyl bromide, if you get it into the environment, because there's nucleophiles everywhere, we're on a water planet, water's a nucleophile, it doesn't stick around very long. It'll turn into methanol, and bacteria can eat methanol and turn it into CO2. So, yeah, interesting. Are they both the final product or only the one circled? The only one that's the final product that I'd want you to draw is the one that's circled, which is what came of the substrate in your first step. Thanks, Michaela. Next reaction. Okay, let's draw this thing out. CH3, 3 CH3s and a Cl. And this one also is with acetic acid. What's our starting alkyl halide? Methyl primary, secondary, tertiary. Yep. And again, no strong alkoxide, no strong nucleophile, but we have a protic solvent. Same thing, acetic acid. So if you go way back up, we have a protic solvent only, and tertiary, we have SN1 or E1 if heat. Did we have heat there? No heat. This is SN1. Okay. So first thing, for SN1, we lose our leaving group. And our nucleophile is going to be our solvent. We have acetic acid. We're going to use the OH as our nucleophile. I think we just did one like this, didn't we? Did we do this exact one? No, we did an SN2 before. Make that thing go up. We need to remove that extra proton, and to do that, we're not going to use chloride, awful base. We're going to use our solvent again. It feels weird using an acid solvent, acidic solvent, as a base, right? It's not a very good base, but it's better than chloride. And there's a hell of a lot more of it in solution than chloride, because this is a solvent. Solvent, like for water, if water is a solvent, the concentration, the molarity of water in pure water is like 55 moles per liter. So it's like really high compared to the chloride, which is going to be like, you know, way less than 1 molar. Okay, so this is going to come in as a base just like before. And we get another ester. We're not going to bother drawing the other products. This is the one we're interested in. Cool. Easy stuff, isn't it? Look at that heat. So we have the same one. Still tertiary. Now we got heat, so heat does the same reaction. Well, not the same reaction, it does E1. Well, E1 and SN1 have the same first step anyway. E1 does elimination. So that means it removes a hydrogen from a beta carbon. Alpha, beta, beta, beta. It's tertiary carbocation. We need to pick any one of our beta carbons. It doesn't matter which, because they're all the same. They're all CH3s. And I'm going to just draw the hydrogens out on the one of them that we're interested in. And now we're going to use our solvent as a base, just like before, except now we're going to pull off a beta hydrogen. Pick any one of those you like, and you get this, and that's it. Side products are chloride, and you got this, this. This has a resonance structure, which can put the double bond in the other way. So it's not that bad. It's not as bad as it looks. But yeah, it's still a pretty strong acid. That's it. This is what you make by elimination. All right. Starting alkyl halide, primary, secondary, tertiary methyl. Primary. Yep, primary. And what are our conditions? CH3OK. Potassium, so we separate them. CH3O minus. K plus somewhere over there somewhere. Is that an alkoxide? Yep. Is it bulky or small? Small. So primary small alkoxide, right to the very top. Primary small alkoxide is SN2. Great. Let's do an SN2. So what we can do, actually, we don't have to redraw anything here. We can just tax the alpha carbon, goes there. I think we were asked to put all our electrons in, so let's put our electrons in the bromide. Careful when you do these questions not to lose carbons. It's very easy to miscount and drop a carbon or add a carbon. The carbon chain you started with shouldn't gain or lose carbons. Not a chiral center, so I mean it does invert, but if it's not a chiral center, you draw it the same anyway. Yeah. It's important that you draw it flipped when it is a chiral center. Yes. Or, yeah. For the following reactions, okay. So, primary, methyl, secondary, tertiary. Secondary. And what are our conditions? Alkoxide, big or small? Small alkoxide, good. Right to the very top. Small alkoxide. For a secondary, E2. Great. So let's draw this out. I'm going to erase those. We're going to take one of our beta carbons and draw the hydrogens in. Do it on the other side too if you like. And E2 involves removing a beta hydrogen and losing the leaving group all in one step. So we're going to use OCH3 minus. This is going to be our base, our alkoxide. It's going to remove a beta hydrogen. CH bond makes our double bond, and bromide goes away. So all happens in one step. Lots of bonding changes here. This, you have Br minus is up here. It's detached. It's the leaving group. Give this. Easy peasy. All one step. clean. It's E2 because it's a bimolecular reaction, two things colliding in the rate determining step. There we go. Four. That time is not right there, by the way. It's not 9:41. It's 9:11. Okay, starting material, primary, secondary, tertiary. Good, primary. What's this big thing now? CH3C is this. CH3COK, we dissociate. So we have that. What do we have here? Nucleophile. Yeah, that's going to be a bulky alkoxide. Bulky alkoxide in primary, let's not look at our table. What is this going to be? E2, yeah. Bulky alkoxides will always do E2, unless it's methyl because there's no beta hydrogens. The E2, very good. That means we have to find our beta carbon and draw in the beta hydrogens. And let's get our big bulky base in there. And we're going to start our arrow at a pair of electrons. It's going to be an acid-base reaction, but the CH bond electrons, because it's E2, goes between those two carbons to make a pi bond, and bromide goes away. And I guess if we want to be complete, we should put our electrons on the bromine. And that leaves us double bond here, bromide, and our alkoxide turned into its conjugate acid. Removed a hydrogen to become an alcohol. Perfect. Here's one, primary, secondary, tertiary. What do you think? You're not stumped on this one. Secondary, good. And NaI, that's not an alkoxide, but it is negatively charged. It's I minus is really what we should be thinking when we see NaI. It's a strong nucleophile and secondary. And if you look at the table, that gives you SN2. Great, let's do SN2. And we have iodide. SN2, you always draw them the same, right? Find the alpha carbon. It attacks the alpha carbon. The leaving group gets the bond, the pair of electrons in the bond. And we substitute the chloride for the iodide, but we have to do so with inversion. This is a stereocenter. It's a chiral center. So the Cl, if it's coming forward in the product, whatever attacks, because it attacks from the backside, has to be going back. Inversion, what we would call that. Beauty. Not too bad. How about this one? What kind of alkyl halide is this? It's tertiary, good. We got heat. We've got a product solvent. Everything here kind of looks like it's E1, but it's not. No reaction. Why is this no reaction? Yeah. Fluorine is an awful leaving group. Fluorine doesn't react. Any of these. It has to be chlorine, bromine, or iodine. Okay. I guess astatine too, but it's radioactive. You'd never see that. So yeah, no reaction because F minus is a terrible leaving group. And it's terrible because it's the same size, essentially, as a carbon. The orbitals are the same size. They overlap really strongly. They make a very strong CF bond, and it's very difficult to break that bond. Very stable, these kinds of molecules. Yes, question? Yes. In this course. Yeah. Like, yeah, you drop a nuclear bomb on it, something will happen, but yeah. Under ordinary conditions, yeah. CFs don't do anything. So I could trick you too. I could give you a question like this. Put a fluorine on here and then put like a Cl. You just forget the fluorine. Pretend it's a hydrogen. And do the reaction will be over on this side of the molecule. It's not really a trick. Okay, let's turn it into a more reasonable leaving group. Now we have still tertiary. Iodide's a fantastic leaving group. We have a product solvent, which is, and we have heat. Now we can confidently do our E1. So, redrawing it, leaving group leaves. The arrow starts at the CI bond. Important where you start and finish these things. Plus, and we have water. And we're doing E1, so we need to pick one of our beta carbons, draw in the hydrogens. Plus I minus. Iodine's a good leaving group. That's what E1 would look like for this molecule. Same reaction, except this time we don't have heat. That means it's going to be SN1, right? This is one of these cases where it could be either way, and we push it to E1 with heat, cool it down, and push it towards SN1. SN1 and E1 have the same first step, which is loss of the leaving group. Now we have water acting as our nucleophile. I want a red arrow. And we don't like positive charges in our products, so let's bring in another water molecule. This makes plus we still have the I minus from the first step. Why does water attack in the second step and not iodide? Which is a better nucleophile, iodide or water? Iodide, yeah. Iodide's like 1,000,000 times better. But if you did, all you'd do is go back to where you started. And then it could just break apart again. So what might be correct is to draw this first step as an equilibrium, back and forth. The other thing water has going for it is it vastly outnumbers iodide in concentration. So you can even if something isn't as reactive, you can compensate by jacking up the concentration to make that reaction faster. Okay. How many more of these do we have? A couple. But you know what? It's 9:21, which means the class is over. You can leave if you want, but I'm just going to finish this because this is just review anyway. It's not like I'm trying to cram in more material. So yeah, if you don't feel like sticking around, you don't have to. You don't have to be here at all anyway, but let's finish these ones because this is, I think, good for you to have available in a single place. So we have a starting compound here, which is secondary, and we have a product solvent, and we have heat. Go right back to the beginning. These, again, are conditions for E1. E1, by now, you should have the first step in your head is loss of the leaving group. The nice thing about these is it seems complicated, and there's a lot to remember and a lot of steps, but it becomes super automatic after a while. It's like Lewis structures maybe seem crazy when you first look at them, but then you realize it's just a stepwise procedure, and you use the same procedure every time. These are easier than Lewis structures, I think. Maybe not. So we got our cation. E1, we have to pick a beta and draw the hydrogens in on the beta. And we're going to use our alcohol here, our solvent, as our base. And second step is this. Br minus. I lost some electrons there. There we go. This is one of the ones, a little more colorful, came from the Instagram account. Okay, primary, secondary, tertiary methyl. Tertiary. Our conditions are conditions for what reaction? These are alkoxides. That's what's in our heads. Get rid of the sodium plus. Don't worry about the neutral solvent. It's going to be this thing that's going to be doing our reactivity. We have a small alkoxide and tertiary, which means it's going to be E2. I'm going to redraw it down here. Pick one of our beta. That one's their alpha. This one's their beta. And bring in our alkoxide. Like that. The CH bond breaks and goes there, and the electron pair goes up to the bromine. That gives us this. Br minus is kicked out, and this. We draw these all day. Just for fun. Next one. What kind of alkyl halide is this? Methyl primary, secondary, tertiary. Yeah, this one's tertiary. How do you know? Well, we have our alpha, we have our beta, 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 and that conditions. What do the conditions look like? Strong nucleophile. In a polar A product solvent, DMSO, those conditions scream SN2 to me, but if you look at a tertiary alkyl halide, it's not going to do an SN2. It's not going to do elimination because we don't have a base, so it's going to do SN1. So we have to first kick out our leaving group for SN1. Make a carbocation. You always make carbocations in SN1 and E1. And then we have iodide. it can now, I don't like that. I want red. And that's it. Two steps. So that's a bunch of examples, and I think we've sort of hit every possible variation of these questions. We did all 4 mechanisms. We did all 4 sets of conditions. I don't know if we did 16 examples. I don't know if we hit every single square, but I think we hit the majority of them. Yeah, so that's where we're at. I just wanted to have a quick comment on the midterms so far. The average, I think, for the other section was around 70 for the written part, a little bit higher for the multiple choice, like 74, 73 for both sections. Our section is also looking like it's around the same place. I still have another question to go, so I can't really see. If it wasn't for the resonance structure question, the class average might be 80. That was an outlier. That question was, on the whole, very poorly done. The average for that question in the class was 60%, where all the other ones were above 70. So that's, you know, if you put them all together, we're around 70. But yeah, I might have to put together a little tutorial video on how to do resonance structures, because I think there's a lot of people that aren't super comfortable with that yet. Yes, Miranda.
So do you think our marks will be back for the written test?
Probably today.
Today?
Yeah, I expect it to be done today. Yeah. Great. Thanks, everyone. And I'll see you next Monday. Enjoy your break.
Dr. Lukeman.
Yes. Who am I talking to?
Tristan.
Sorry, yeah, can you say that again?
It's Tristan.